What specific problem does your proposed method, particularly the exploration of Euclidean geometry in contrastive pre-training, aim to solve, compared to existing approaches like CLIP and Meru?
The proposed method aims to address the limitations of existing approaches like CLIP and Meru by exploring the effectiveness of Euclidean geometry in contrastive pre-training for language image models. Unlike CLIP, which utilizes cosine similarity and L2 normalization, the exploration of Euclidean geometry allows for the use of negative Euclidean distance squared as a similarity function, which potentially enhances performance through implicit L2 regularization. The findings indicate that Euclidean CLIP, EuCLIP, not only matches but can exceed the performance of CLIP and Meru, while also supporting hierarchical relationships effectively. Additionally, the study highlights that the final layer norm in transformers degrades performance, suggesting that removing it can lead to better outcomes. Overall, the method seeks to provide a more intuitive and effective geometric framework for contrastive learning, challenging the prevailing reliance on hyperbolic embeddings.
How does the proposed method or algorithm work? Illustrate it step by step, particularly focusing on the modifications made to the softmax logit and how distance metrics are implemented in the context of the different geometries explored.
The proposed method involves systematically testing various embedding geometries for contrastive language image pre-training models, specifically focusing on modifications to the softmax logit and distance metrics. Initially, the method employs cosine similarity as the softmax logit in the CLIP model, which is linked to the Euclidean geometry of the embeddings. The paper introduces alternative distance metrics, such as negative geodesic Arcos distance for elliptic geometry and negative Lorentzian distance for hyperbolic geometry, enhancing the model's ability to capture hierarchical relationships. In the case of Euclidean geometry, the method explores using negative Euclidean distance squared as the similarity function, which incorporates implicit L2 regularization and improves performance. Ultimately, the findings indicate that the Euclidean CLIP EuCLIP model, utilizing these modifications, matches or surpasses the performance of the original CLIP and the more complex Meru model, demonstrating the effectiveness of the proposed adjustments.
Can you provide a simple yet illustrative example that demonstrates the inner workings of the proposed algorithm, especially how the distance metrics in Euclidean geometry differ from those in hyperbolic geometry?
The proposed algorithm contrasts Euclidean and hyperbolic geometries through their respective distance metrics. In Euclidean geometry, the distance between two embeddings, x and y, is calculated using the formula xy, which is straightforward and intuitive. For instance, if we have 2 points in a 2D space, the Euclidean distance would be the straight line connecting them. In contrast, hyperbolic geometry employs the Lorentzian distance, which is more complex and involves the Lorentzian inner product, resulting in a distance metric that accounts for the curvature of the space. For example, when embeddings are lifted onto the Lorentz hyperboloid, the distance metric reflects the hierarchical relationships more effectively, as it can represent more complex structures like trees or networks, which is particularly useful in modeling relationships in language image tasks. Thus, while Euclidean distance is linear and direct, hyperbolic distance captures the intricacies of relationships in a non-linear fashion, enhancing the model's ability to understand and represent hierarchical data.
What are the theoretical or practical benefits of replacing L2 normalization with distance squared logit as you explored, and how does it enhance the performance of the model over traditional methods?
Replacing L2 normalization with distance squared logit offers both theoretical and practical benefits, as highlighted in the paper. Theoretically, using distance squared logit introduces an implicit L2 regularization term on the positive pair, which can lead to a better distribution of the L2 norm and improved representation of embeddings. Practically, the experiments demonstrated that this approach outperforms traditional methods, such as cosine similarity, particularly in Euclidean geometry, where the final layer norm of the transformers was found to degrade performance. The distance squared logit also allows for a more stable training process, as evidenced by the superior performance of EuCLIP compared to CLIP and Meru across various zero-shot metrics. Overall, this method enhances the model's ability to support hierarchical relationships and improves its generalization capabilities in contrastive learning tasks.
How is the method validated or tested? Specifically, explain the experimental design, the datasets used for training and evaluation, and the metrics employed to demonstrate the effectiveness of your proposed approach.
The method is validated through systematic experiments using modified EuCLIP and various embedding geometries, specifically focusing on the Euclidean geometry model, EuCLIP, and comparing it against CLIP and Meru. The training is conducted on small and medium-scale datasets from DataComp, with the small scale using the top 30% of examples based on CLIP scores and the medium-scale filtering for examples clustering around ImageNet classes. Hyperparameters are tuned at the medium scale using the VIT-B32 model, and the best-performing model is scaled to VIT-B16 for head-to-head comparisons. The effectiveness of the proposed approach is demonstrated using zero-shot metrics, where EuCLIP consistently outperforms both CLIP and Meru across all metrics evaluated. Additionally, qualitative assessments of embedding space structures and distance distributions further support the findings, indicating that the separation between text and image embeddings is influenced by the model's architecture and training methodology.
What are the limitations or drawbacks of your proposed method, particularly in the context of how the final layer normalization affects model performance and the implications this has on the overall architecture?
The proposed method, particularly the EuCLIP model, faces significant limitations due to the inclusion of the final layer normalization lane. Our experiments indicate that restoring the final lane drastically impacts model performance, with the VIT-B16 final lane barely outperforming the VIT-B32 no-lane model, despite the latter having 4 times the number of patches. This suggests that the final lane constrains the model's degree of freedom, preventing it from fully leveraging the embedding space. The findings imply that the final embedding must reside on a hyperellipsoid, which limits the model's ability to adapt and learn effectively. Consequently, this architectural choice may lead to the rejection of potentially novel model architectures or loss terms, as their performance could be adversely affected by such incompatibilities.